So last time or the time before we had estimated the integral from 2 to 6 of the natural log of x dx using n equal to 4 trapezoids. And we got something, doesn't really matter. I'll remind you that our estimate, actually, I'll remind you of the formula just to remind everyone of the formula. So the way we found this was by doing T4 was equal to our delta x over 2 times f of the first x value plus 2 times f of the next one plus 2 times f of the next one plus 2 times f of the next one plus 1 times f of the last one. I know it's the last one because I know that n is equal to 4. So if I draw my little interval here from 2 to 6 and break it up into 4 equal subsections, my delta x is 6 minus 2 over 4, which is 1. And then I have exactly 5 endpoints. 1, 2, 3, 4, 5. You have 4 intervals, you have 5 endpoints. And then it's a 1, 2, 2, 2, 1 pattern. The last one, the first one, you get a 1 coefficient. The other 3, you get 2s. And so in this example, this would end up equaling delta x over 2. And then you have the natural log of 2 plus 2 times the natural log of 3. Sorry, it's a little messy here. Plus 2 natural log of 4 plus 2 natural log of 5 plus natural log of 6. You bust out a calculator and you get approximately 5.34. But that's the trapezoid formula, right? Take your delta x, divide by 2, and then do your 1, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern. If it's n equals 4, it's going to be literally 1, 2, 2, 2, 1. If it's n equals 8, you'd have 9 things to be 1, 7, 2 coefficients, and then 1 at the end. But then the other thing, let me speed this down just a little bit. I don't love that. Or let's just up, I guess. Oh my gosh, can I do it the right way? Maybe not. Okay, there we go. The other thing we sometimes talk about is how good our estimate is. So we would like to see over here. Maybe not. Yeah, of course, yes, anytime. Please don't hesitate to ask me to modify you being able to see things, or yeah, always happy to change things around. So the other thing we want to do is we would love to put an upper bound on the error of our estimate above. So here's the formula for the trapezoid error upper bound. The error using the trapezoid method is always going to be less than or equal to your b minus a cubed over 12 times n squared times the absolute value of the maximum of the second derivative of your function, where the values you're allowed to plug in have to be in your interval. Sometimes it's really easy to know what this maximum is. Sometimes it's a little bit less easy. But let's do this example. So our function, we're looking at the interval from 2 to 6 of natural log of x dx. So our function is the natural log of x. The first derivative is 1 over x, or x to the negative 1. The second derivative is negative x to the negative 2, or negative 1 over x squared. And then we know that x has to be between 2 and 6. Ignoring the fact that this is negative, what value of x is going to make this expression as large as possible? We ignore the negative part for a second. Do I want to plug in x equal to 2 or x equal to 6? Right. We're going to plug in the thing that's smaller because our x is in the denominator. And oftentimes, you're going to have a function where it's as easy to be like, well, pick one of the endpoints, and that's the one that's going to make it the biggest. So here, the absolute value of the maximum of f double prime of x, I feel like you want the, I feel like it's the maximum of the absolute value of f double prime, actually. I feel like that, like, yeah. I mean, it doesn't really matter. Take it, make it as big or as negatively big as possible. The maximum here is going to be right. So it's like the maximum of the absolute value of f double. Yeah, I was like, I feel like I'm writing this kind of wrong. Say that one more time. Oh, sure. Yeah, that's fair. Yeah. And then this should really be here. Right? Yeah. Sorry about that. Let's try that again. So the maximum of the absolute value of the second derivative, where x is between 2 and 6, is going to be exactly the absolute value of -1 over 2 squared, which is 1/4. And then we just throw everything into this formula here. So our error, or the absolute value of our error, is going to be less than or equal to 6 minus 2 cubed over 12 times 4 squared times 1/4. And whoever wrote this question was clearly thinking about making things easy. So be careful here, or I should say, on an exam, I would leave my answer like this. I would probably simplify it only because the simplification is easy. But don't spend your time simplifying if you're not asked to. I've got 4 cubed over 12 times 4 squared times 4. I can cancel some stuff. On the bottom, I have 4 times 4 times 4. On the top, I have 4 times 4 times 4. Those are going to cancel. And I'm left with 1 over 12. So be smart. And this is approximately 0.083. But really, this is how. Here's what I'll point out. The actual error here was like 0.02 or something. But this isn't giving you the actual error. This is giving you the upper bound that the error could have been. So we're just saying we know that the error of our estimate is less than or equal to 0.083. Probably a lot less. Questions about that? Yeah, let's do one other example like this, and then we'll move on to the practice test, I think. And then we'll come back around to the other thing I was going to do. So the other thing you might be asked to do, which is pretty typical for the error estimate questions, is given an interval, how many subintervals do you have to use so that your estimate is good within some sort of margin? So for example, they might ask, find the number n so that the trapezoid rule estimate, so that the t sub n of the interval from 0 to 1 of e to the negative x squared dx is accurate to within 0.001 or 1/1000th, if you like. So great. Let's write out the error formula again. Are you going to be given the error formula? Okay. The opposite value of the error for the trapezoid method is less than or equal to b minus a cubed over 12n squared times the maximum of the absolute value of the second over the interval. Where here x is between 0 and 1. So, oh, and we want this to be less than 0.001. Right? This is what we're going to focus on. So we're going to use this inequality to figure out what n has to be. And before we can do any of that, we have to deal with this maximum of the absolute value of the second derivative. So let's go ahead and deal with that first. So our function is e to the negative x squared. The first derivative is fine. It's e to the negative x squared times negative 2x. The second derivative is going to be a little bit gnarly. It's going to be product rule. So the derivative of e to the negative x squared is e to the negative x squared times negative 2x. And then I have to multiply it by the other negative 2x that's hanging out over there. Plus, leave the e to the negative x squared alone. and multiply by the derivative of negative 2x, which is negative 2. This is where we actually have to do some sort of work. I'm going to factor out an e to the negative x squared. And I'm left with negative 2x and negative 2, which is 4x squared minus 2. Here's what we usually do with something like this. So the hard way to do this would be to take another derivative and set it equal to 0 to find the critical points to actually maximize it. Nobody's doing that. What we're going to do is we're going to take each factor and make each factor as big as possible. So to make this factor as big as possible, we're going to let x be 0 or x be 1 or something in between. Right. And that, technically, I guess you could really argue 0 or 1 would actually both equally work, because 0 minus 2 would be negative 2, and then we'd get rid of the negative sign. But I would pick 1. I'm thinking for this piece here, I'm letting x equal 1 to make it as large as possible. So this part here is equal to 4 minus 2, which is 2. And then for this part here, I'm going to let x equal 0 to make it as big as possible, because e to the negative 1 is smaller than e to the 0. Think about the graph of e to the x. E to the x gets larger as you move to the right, smaller as you move to the left. So here, we're going to let x equal 0. It's perfectly fine to do this. We're picking and choosing the points for kind of each factor that makes each factor as large as possible to make sure that we for sure have an upper bound. This is definitely a maximum. It might be too big. That's okay. It's okay to be too big. It's not okay to be not big enough. So here, we're going to say that this is definitely, yeah, I'm going to write this way. Yeah. 1, right, e to the 0 times 4 times 1 squared minus 2, which is just 1 times 2, which is 2. And that's what's going to go in here. So all this here, that's going to be 2. Is it actually 2 in reality? No. But we don't care. Great. So now that we've dealt with that, we can deal with the rest of it. So let's plug in all the things. What's the thing we're trying to solve for? Right. So we should be able to plug in for everything except for n and then solve for n. So we're going to have b minus a, that's 1 minus 0 cubed over 12 times n squared times 2 is less than, I would much rather use a fraction here. I would much rather write 1 over 1,000. Let's simplify this. On the left-hand side, we have 1 times 2 over 12. That reduces to 1 over 6. So I can write the left-hand side as 1 over 6 n squared is less than 1 over 1,000. I always like to cross multiply here, but really I'm doing too much work when I cross multiply. I would really like to say I have like 1,000 less than 6n squared, but I really should have just left the 6 on the other side. I should have really just multiplied this side by 1,000, this side by n squared, and gotten 1,000 divided by 6 is less than n squared. It's perfectly fine to cross multiply here, and we don't have to worry about the inequality changing directions because everything we're multiplying by is positive. 1,000 is positive, n squared is positive. And then finally, take the square root of both sides, and we say, okay, great. N has to be bigger than the square root of 1,000 over 6. And without a calculator, that's as far as I can go. I cannot do anything else if I don't have a calculator or a way of approximating that. Unless it happens to, like, if this was like 1,000 divided by 10, then I'd have 100, and the square root of 100 is 100. So look for something here that might simplify easily. Here, I mean, if you use a calculator, you get this about 12.9. So you would get that n is bigger than 12.9. So then we would say that n should be what? Not 12.9. You got to bump it up to the next integer. So we're going to say that n has to be 13. So if n is 13 or larger, the estimate using 13 trapezoids will be accurate to within 0.001. That's the idea. But I would leave my answer like this. Questions, comments? The hardest part about this particular problem is this deal down here, is finding what to bound that by. Often you'll have an easier function where it's easy. Like, so some other examples of things that come up here is like if your function is sine or cosine, you start taking derivatives of it. We know that sine and cosine are always bounded between -1 and 1. So often finding a boundary for that is not too terrible. Usually just 1. All right, let's take a look at his practice exam. And then if we have time at the end, we'll come back around and do some table questions. Where did I put it? It's somewhere over here. It's right there. Cool. I guess I can just write on it, right? I don't have to use it. Yeah, that'd be the smart way to go. Just write on the actual practice exam. Write my own. So, practice exam problem 1A. Let's talk about what we see. I see a mixture. I have x to a power, an algebraic or any power of x term, and a natural log term. We have a mixture. We're going to do one of two things. What's one method we might try to use here? U sub is definitely one thing. What's the other method we use when we have a mixture? Exactly. If you see a mixture, those are the two things you should be thinking. It's either a U sub or it's integration by parts. So I always try to look for the U sub first because it's usually easier. But here, that's not going to work. Right? If you let u equal the natural log of x, your du is 1 over x. I don't have a 1 over x. It means u sub is probably not the way to go. If you are sure that u sub is out, you can bypass it and be like, we know it's going to be integration by parts. Now be careful here. For some reason, a lot of people really, when they start doing integration by parts, if they can, they want to let u equal like the x to a power. And that's not the right choice if you have a logarithm. If you have integration by parts, you should always be letting u equal the natural log if you have a natural log. So we're going to let u equal the natural log of x. dv has to be the entire rest. So if you cover up the natural log of x, everything else that's left is the x to the 4th times dx. Your du is the derivative of the natural log of x, and you have to multiply by dx. Your v is the antiderivative of x to the 4th, which is x to the 5th over 5. And this integral is going to be equal to uv minus the integral of v du, which is going to be u times v minus the integral of v times du. The whole point of this process is to make your new integral simpler, and this is a lot simpler if we make a couple quick changes, or not changes, but like simplifications. We should write this as the natural log of x times x to the 5th over 5 minus, we should pull out the 1/5, and we should definitely simplify x to the 5th divided by x is just x to the 4th. And then we're almost done. We're going to get the natural log of x times x to the 5th over 5 minus 1/5 times the integral of x to the 4th is x to the 5th over 5 plus c. And yeah, you can make that look nicer, but again, I'm not worrying about simplifying things unless specifically asked to. I should really say you're not worrying about things unless simplifying things unless specifically asked to. That should be what you take to heart, right? Don't simplify unless you need to. Okay, this one. You have a natural log of something. I think we have to just do straight integration by parts here. Not that we didn't do that before, but what I mean here is this one may be a little bit less obvious, but we probably have to let u equal the natural log of 2 plus 2x for integration by parts, and dv equal dx. And really the reason I know that I should do it this way is because I know that when we integrated the natural log of x before, this is how we did it. We used integration by parts and we let u equal the natural log of x and dv was just dx. This one's probably going to work the same. It might be a little less nice. We'll find out. Our du is going to be 1 over our stuff times the derivative of the stuff, and the derivative of the inside stuff is exactly 2. And there's a dx there. And our v is going to be the antiderivative of 1, which is x. Now, even though I don't want to simplify my answer, if there are simplifications I can do along the way to make my life easier, I do want to do those. I'll point out that here, I can rewrite this as du equal to just 1 over 1 plus x. So I can factor out the 2 from the bottom and cancel it with the 2 that's on the top. Okay, we're going to throw the formula at it. So our integral is going to equal, you don't have to write out the uv minus the integral of v du. I might do it once, but then not do it again. I'm going to get u times v. I would probably write the x part first. So x times the natural log of 2 plus 2x minus the integral of v du. Ooh, x over 1 plus x. You could say x times 1 over 1 plus x, but it's really just x over 1 plus x. Oh yeah, someone was asking about this the other day. So how do we deal with x over 1 plus x? There's a couple ways you can deal with this. I personally would choose to do the polynomial division. When I see a rational function where the degree on top and the degree on the bottom are the same, I do polynomial division. But sometimes people like to do like tricky things that also end up getting the same result. I'll point out there's a couple ways of dealing with this. You can either say that, let me write it on the side here so I don't like cover all this up here. But you could either say that x over 1 plus x is equal to 1 plus x minus 1 over 1 plus x, right? I've just added and subtracted 1, didn't change anything. But then you can break this up as 1 plus x over 1 plus x minus 1 over 1 plus x, which is really 1 minus 1 over 1 plus x. That's one way of getting it. And then this is something we can integrate. Or you can do the polynomial division. X divided by x plus 1. X plus 1 goes into x one time. 1 times x plus 1 is x plus 1. Subtract x minus x is 0. 0 minus 1 is minus 1. So this ends up equaling your quotient 1. Sorry, that's terrible. Plus your remainder over your divisor. Oh, it's the same thing. 1 minus 1 over x plus 1 is the same as 1 minus 1 over 1 plus x. So either way you want to do it is fine to make sure you're able to do it. So then back to the problem we're actually doing, this is going to end up equaling x times the natural log of 2 plus 2x minus the integral of 1 minus 1 over 1 plus x, which is going to end up giving us x times the natural log of 2 plus 2x. The integral of 1 is just x. The integral of 1 over 1 plus x is the natural log of the absolute value of 1 plus x. Is it a minus or a plus there? It's a plus. It's a minus, a minus. Oh, it's a little funky, I'm not gonna lie. So it's a little bit with a kind of a lot there to deal with. All right. It's interesting, like I'm intrigued by this first problem because if I was giving a problem where all the problems were integration by parts, I feel like that's almost misleading. Like, here's a bunch of problems. I'm not telling you how to do them, but they're all the same method. I mean, that feels like I would feel like I was being tricked. Okay, but this last one's definitely also integration by parts. I would say let's do the integration by parts without the limits of integration. So for the integral of x e to the 3x, we're going to let u equal x. Du is 1 times dx. dv is e to the 3x dx. V is 1/3 e to the 3x, or e to the 3x divided by 3 if you prefer. So then our uv minus the integral of v du is x times 1/3 e to the 3x minus the integral of 1/3 e to the 3x dx, which becomes x times 1/3 e to the 3x minus 1/3 e to the 3x divided by another 3. So that'll be 1/9 e to the 3x. So then over here, I would say, great, this is going to equal that integral. And I might rewrite it as x over 3 times e to the 3x minus 1/9 e to the 3x, evaluated from 1 to 2. I think that is how you should do this problem. You do the antiderivative over here because it's kind of complicated. And then over here, take whatever your final antiderivative is. You don't need a plus C here. And use the fundamental theorem of calculus to plug in the top and the bottom. So then doing that, we're going to get 2/3 e to the 3 times 2 minus 1/9 e to the 3 times 2 minus 1/3 e to the 3 minus 1/9 e to the 3. Don't simplify this. I know it's really tempting. I really want to simplify it. I really want to write that this is 6/9 minus 1/9, which is 5/9 e to the 6, and this is 3/9 minus 1/9, so it's 2/9 e to the 3rd. Don't do that unless someone is telling you to do that. I wonder what the instructions say on the test, actually. Now that I keep saying that. There are 6 problems. There are 6 problems. Make sure you have all 6. Violation of university honor code, no notes, books, or phones, etc. Is expected your phone's on silent. Cool. Read directions. Do problem carefully. Show all work. In most cases, the correct answer with no supporting work will receive little or no credit. Neatness as well as proper use of mathematical notation will be factored into the grading. You'll be graded on correct use of limit notation where applicable. Answers must be written without negative exponents and fractions of fractions. Okay. So notice in there, nothing else that says you have to simplify. I mean, I would say it is expected that any student in calculus should know the integral. That is an expectation that is fair unless you're taking the 19 series. But that's not what you're taking. So I mean, do you actually need to know it for this test? I don't know, because I don't know what he's going to ask. But could he ask you something where you're expected to evaluate like cosine of pi over 3? Yeah, that's a fair, valid question. Is he going to? I don't know. So some more integrals here. So I'll point out this first question is missing an integral symbol. Right? I see a dx at the end. I'm missing a integral there. I'm sure it was an oversight. If that happens on an exam, I would encourage you to ask, right? Did you mean to have an integral symbol here? Instead of just this, instead of just this. So since the first page was all integration by parts, I'd be willing to bet that the second page is going to be all u substitutions. That's probably a good guess. That doesn't mean we should avoid other things. But like if we're talking trig here, that's kind of all we got is u substitution. So when you have things with sines and cosines or tangents and secants or cotangents and cosecants, it's usually picking u equal to one of the trig functions, just bare bones on some, right? You're not going to let u equal sine squared. You're going to let u equal sine of x, or you're going to let u equal cosine of x. Excuse me. Or you're going to let u equal cosecant, or u equal cotangent, or secant, or tangent. So here, I'm either going to pick u equal to cosecant of 5x, or u equal to cotangent of 5x. Let's think about which choice is better. So if you were to be cotangent, what's the derivative of cotangent of 5x? Right. It's actually negative cosecant squared of 5x times 5. But the important thing to focus in on there is the cosecant squared. And that's probably not going to work out great because I have a cosecant cubed. And if I do that, I'm going to have a leftover cosecant, and that's problematic. On the other hand, if I let u equal cosecant of 5x, the du is negative cosecant of 5x times cotangent of 5x times 5 dx. And I'm happy about this because after I've dealt with my du, that's going to soak up one of the cosecants and the only cotangent. There'll be a cosecant squared left over. But if u is my choice, or if cosecant is my choice for u, then that leftover cosecant squared will just be u squared. So here's what I would do. I would do a little manipulation over here. I would say that negative 1/5 du is equal to positive cosecant of 5x times cotangent of 5x dx. And then over here, I would rewrite the integral as the integral of, I want a cosecant cotangent at the end. So I'm going to write cosecant squared of 5x times cosecant of 5x times cotangent of 5x dx. So that now we can see that this part here, that's equal to our -1/5 times du. And we're always trying to deal with the dx du changeover before we do anything else. And then what's the cosecant square going to be? There's no dv here. So I'm doing a u sub. I've dealt with my dx du. And my u was cosecant. So cosecant squared gets to magically transform into exactly. And now we're pretty psyched because we can rewrite this integral. I'm going to put the -1/5 out in front as -1/5 the integral of u squared du. Straight up power rule, we get -1/5 times u cubed over 3 plus c. I would rewrite this as -1/15. And then we do need to change back from u to x. So we're going to plug back in that u is equal to cosecant. So you're going to have cosecant cubed of 5x. That's an interesting question here. Oh, sorry, this stuff's in the chat. I keep missing it. I apologize. Sorry. Oh man, I was looking for the chat and like it disappeared. I apologize. There's questions here. Let me take a look at them real quick. Sorry, those were a minute ago. Oh, sorry about that. Yeah. Let's see. How did you do? So sorry to answer some questions from a while back. I knew it was 1/4 for that question. Sorry, let's back up for just a minute. I'm sorry. If I'm not answering something in the chat, you're welcome to unmute yourself and say, "Hey, James, there's a question in the chat." And I usually try to look, but I had it kind of covered up, so I didn't see it. I'm sorry about that. So just to back up for a minute here, the way we knew that we had a 1/4, which was, I believe you're referring to the maximum of f double prime here in this problem we did way back when. The way we knew it was 1/4 is we're trying to make this as big as possible. And we're trying to make that as large as possible. If I plugged in 6, I'd have -1/36. If I plug in 2, I have -1/4. I'm taking the absolute values. If I plug in 2, I have -1/4. Sorry about that. This is 136, which is smaller. This is 1/4, which is bigger. So that's how I'm getting the 1/4 there from way back when. Sorry about that. And then somebody else asked, could you explain where each -2x is coming from? That was a little bit later. Oh, sure. Yeah, like sure. Oh, okay, yes. Good, fair question. Again, sorry. Feel bad. So here, if we call this F and this G, this part right here is your F prime because of the chain rule. And this part right here is still your G from before. And then this part here is your F. This part here is your G prime. And finally, that last question, I'm not going to be able to answer quite as well because the question was, why won't U sub work here? And that question could have been for any of the integration by parts problems we've done so far. So I'm not sure which one you mean, but I'll just, I actually, if you can tell me which question you meant for that U sub part, I would be curious to know because I'm not really sure. So if you want to clarify that for me, whoever that is, sorry, Tia Block. If you want to let me know what question you were asking about the use of from problem 1A part B. Oh, sorry, 1AB. Yeah. So I will say for 1AB, so do you specifically mean the original integral, or do you mean when we got to this x over x plus 1 here? Okay. So the original, you could actually start off with the u sub. It would be perfectly fine. Let me use this other piece of paper I had here before that I was writing notes on here. It would have been acceptable in the beginning to say, gosh, could I keep anything in order here? There we go. Yeah. We could have said in the beginning, if I have the integral of, what was it, natural log of 2 plus 2x, you totally could have done u equal to the insides here. Du is 2 dx. 1/2 du is equal to just dx, and then rewritten this as the integral of dx is 1/2 du, and then the natural log of u. But then for that integral, you still have to use integration by parts. It is the only way we have to integrate the natural log of x or the natural log of u. So knowing that I was going to have to use integration by parts anyway, I decided I should just skip the not really super necessary u substitution and get started with the integration by parts. So that's why that's working out. Okay, hopefully I'll pay a little bit better attention to the chat. Let's continue on. And let's continue on trying to keep your papers in order. Okay, so next question, sine x over cosine squared x. So this also falls into the, we're going to let u equal sine or cosine. What's the right choice here? Are we going to let, so let me see some thumbs. I want a thumbs up for letting u equal sine. I want a thumbs down for letting u equal cosine. What do you all think? Sine or cosine is my choice for you. Think about what your du is going to be, and if you have that. Right, so if you pick, I'm gonna say the wrong thing first. If I already pick u equal to sine, it's not going to work out because my derivative is going to be cosine. And so my du is cosine of x times dx. And I want to make it super extra clear. We do not have cosine of x times dx. We have 1 over cosine squared times dx. This is not going to work. So we're going to let u equal cosine. Again, not cosine squared, just the cosine function. And then our du is going to equal negative sine of x times dx. So that negative du is equal to positive sine of x dx. And now we're ready to start changing things. If it were me, I really, as you've seen many times, I really like to break up the part that's going to play the role of du and the rest of the stuff. So I would rewrite the integral as 1 over cosine squared of x times sine of x times dx. And I say, great. This sine of x times dx is equal to negative du. This 1 over cosine squared is equal to 1 over u squared. Now be careful. I really, really don't want you to write it like this. I'm going to write it, I'm going to cross it out. If you write it like that, it looks like you have 1 over u squared and you're subtracting du from it. You should never be adding or subtracting du. You're always multiplying by du. This is really 1 over u squared times negative du. But I really, really, really would just put the negative out in front, right? As negative 1 over u squared du. Or negative integral of u to the negative second, which is going to then give me negative u to the negative first divided by negative 1. The negative out in front and the negative one you're dividing by cancel out, and you're just left with, sorry, don't forget plus c, which is u to the negative 1 plus c, which is going to be cosine of x to the negative 1 power plus c. But he said we didn't like negative powers. He did say we can't leave with negative powers. So I definitely need to rewrite this as 1 over cosine plus c. Or probably preferably secant of x plus c. I imagine that's how he would prefer you write your answer here. This problem you could have done in a much trickier way. You could have, if again, so doing it this way is the right way. It's the way that he expects you to do it probably, because it's harder to see that you could rewrite this as the integral of 1 over cosine times sine over cosine, which is just the integral of secant of x times tangent of x. And the integral of secant x times tangent x is just secant x. That would also be an acceptable way of answering this question, but it relies on your ability to see that that's what's going to happen. And that's less, it's just less typical, right? Like I wouldn't see that normally. Unless I got to here, I'm like, oh, well, that must have been the derivative of secant, which is secant times tangent. So don't look for those things because they might not be there, but if you happen to notice something, it's totally fine to use that. All right. And then this last question is going to defy my expectations in that I was assuming everything was going to be a u sub. This last one's definitely not a u sub. This last one is definitely integration by parts. We have a mixture, but there's no good choice for a u sub. If you let u equal 5x, your du is 5, that x doesn't get dealt with. You let u equals sine, your du is cosine. I don't have a cosine. This is definitely integration by parts. Really, when you're looking for integration by parts versus u sub, integration by parts, you're kind of applying if you have things that are just straight up multiplied together, whereas u sub, you're looking for kind of a composition of functions. That's why, yeah, but even then, that's not a great example. So I'll just say, I'll leave it there. So here we're gonna let u equal, is u equal to x or is u equal to sine of 5x? Good question. U is definitely equal to x, right? If I use our late acronym, x is the algebraic or the any power term. Our dv is the rest. Also, look here, again, we have a little mistake, a little typo in the problem. There's a dx. That shouldn't be there. If you see typos, ask about them. Not to like point out that he's made a mistake, just to clarify, like, what do you actually want me to see here? Because sometimes people make mistakes and they meant something totally different. Unlikely here, but still worth clarifying. Our dv is sine of 5x dx. Our derivative, the derivative of x is 1 times dx. Our antiderivative of sine of 5x is negative cosine of 5x divided by 5. Okay. Now we're going to use our formula. uv minus the integral of v du is equal to u times v. So x times negative cosine 5x over 5 minus the integral of v du. I would do a little bit of rewriting before I actually found the final answer. So I would rewrite this first part here as negative 1/5 x times cosine of 5 of x, cosine of 5x, minus a minus is plus, and I'd bring out the 1/5 integral of cosine of 5x. And then finally, I'm going to get negative 1/5 x cosine of 5x plus, well, so the integral of cosine of 5x is going to be positive sine of 5x divided by another 5. So I'd have 1/5 times sine of 5x divided by 5 plus c. And yes, you could have written this part as sine of 5x divided by 25, but we didn't need to. All right. Moving right along. Stop me if you have questions. Use integration tables to evaluate. Great. I'm printing them out. So let's take a look here. X over 1 plus e to the x squared. So I'm just looking at something that has a form involving e to the u. So let's go ahead and look at the forms involving e to the u. This is my table. I might not have, do I have the ones I need? E to the u. Okay, great. So I'm looking for one that has a fraction. And I'm looking at this one right here. 1 over 1 plus e to the u du. That looks plausible. So this one's going to require a u sub before I can use this formula. Here's how I would do this. I want to be able to use the formula. I'm just going to write down here that the integral of 1 over 1 plus e to the u is equal to u minus the natural log of, sorry, where'd you go? 1 plus e to the u plus c. So what I'm going to do here is I'm going to make the u substitution. I'm going to let u equal the thing that's in the spot that I want the u to be. So what am I going to let u equal here? I know you all know it. What's u going to be? It's going to be x squared. It's a good choice for a multitude of reasons. It's where I want the u to be in the formula. It's also a thing whose derivative is essentially in my integral. Du is equal to 2x dx. 1/2 du is equal to x dx. So I can rewrite this integral as the integral of 1/2 over 1 plus e to the u du. We probably don't really need to, but I'm going to bring out the 1/2 and get 1/2 times the integral of 1 over 1 plus e to the u. And I'm just going to throw the formula in there. So this is going to end up equaling 1/2 times the integral of 1 over 1 plus e to the u is all this jazz. It's u minus the natural log of 1 plus e to the u plus c. You don't need the plus c in the brackets. And then finally, I think this step gets skipped in a lot of the solutions. Like they just jumps, like this step I just wrote. I feel like they often skip that and they're just like, yeah, we're going to use the formula and then we're going to plug in that u is equal to x squared. But then we're going to do that here. We're going to do 1/2 times x squared minus the natural log of 1 plus e to the x squared plus c. So sometimes with these integration table problems, you first have to do a u substitution before you can apply the correct formula. That's, in my opinion, the best way to approach it. Stop saying in my opinion. Everything I say is in my opinion. That's not true. I guess sometimes I say things that are like facts, not just my opinions. But when I'm saying something is the best way to do it, the caveat is always in my opinion. There might be a better way for someone else, but for me, I'm always doing it the way that works best for me. Which hopefully is also true for you. Okay. So question B here, I've got the natural log of 5x squared. I'm looking for something with a natural log in it. So let's go look at my tables here. And I assume like on the test, I would assume for like this question, he'd just give you the section that has the natural log formulas in, right? Because you don't have to look through the rest of them, I hope. 50? Okay, that's not unreal. But again, they should be by sections, right? So like I'm looking here, and at the top of this, I'll point out they're grouped with things that have u to the n, and then a plus bu, a square root, a square root, something squared. Down here, natural log is the last form. So I'm gonna look at the last part of the table because they're written in order. So looking over here, the last part of the table. I have the natural log of u, I have u times the natural log of u, I have u to a power times the natural log of u. But here I just have a natural log to a power. There's no u in front or x in front. So it's definitely not that one, not that one. I think it's this one, the natural log of u squared. So I'm using this formula here. This one, no, I would still do, I like doing the u sub. So I would let u equal 5x. My du is 5 dx. 1/5 du is equal to dx. So you can rewrite this as the integral of, or should I say 1/5 times the integral of the natural log of u squared du. Now I'm probably going to do more writing here than you really should. So this one actually is probably an example of one where you should cut to the chase, I think. So here, instead of writing out, can you see the formula all right? Over here, instead of writing out u times 2 minus 2 natural log of u plus natural log of u squared, I should actually plug in the value of u here. No, I really disagree. I'm saying that, I know, but I really feel like you should write out the formula so that they know you're using the right formula and then plug it. Or maybe write down the formula number. I think that's not a bad idea. If they should be numbered. I would write out like, okay, I'm gonna use formula number 42. So at least they know that I know that I picked the right formula. And then plugging this in, I'm gonna get, okay, I don't love it, but I'm gonna do it. Yeah. 5x, that's my u, times 2 minus 2 natural log of 5x, that's my u, plus parentheses, natural log of 5x squared. Close the bracket, and then close the parenthesis, and then plus c. Right, there's my u times 2 minus 2 natural log of u plus the natural log of u squared. The reason I'm not writing out the intermediate stuff like I did there is because it's kind of a long formula and I'm trying to save time. So if you can do it this way, that's fine. If you need to write the intermediate step, that's also fine. Just, I know you need to be as efficient as possible with your time because you have a limited amount of time. And finally, 2x over 1 minus 3x squared. So again, I'm looking at forms. So looking at my list here, I'm looking for forms involving like a plus bu, right? A constant plus a constant times my variable. I don't want a square root. I don't want my variable squared. So yeah, it's got to be that one. So that's this first page here, or it might be more than this first page here. No, just the first page, cool. So I'm looking for essentially, so what I'm seeing here, I'm looking for a u over a minus bu squared. I would love it if that was there. right? I'm thinking of this is my BU, this is my U, I'm throwing the two, and this is my A. So do I have a U over A? Yeah, right there, cool. I didn't have a minus, that's all right, I don't need to be a minus because I can adjust. So looking at this formula here, well, first of all, let me do one thing. Let's rewrite this as 2 times the integral of x over 1 minus 3x squared. Yes. So here's what I would say. I'm going to use formula number 4. And looking at that formula there, I would say that my u is x. My a is 1. And my b is what? Good question. My b is -3. That's why I'm adjusting for the negative there. So then I can use this formula 4, and say that great, this is going to equal, I'm going to write down the formula here. 2 times 1 over b squared times parentheses a over a plus bu plus the natural log of the absolute value of a plus bu plus c. And now that I've identified my u, my a, and my b, I can just plug those into the formula. I could have also done that without writing the formula down. So here we're going to get 2 times 1 over -3 squared, which is 9, times parentheses a over a plus bu, so that's going to be -3x, plus the natural log of a plus bu, which is again 1 minus 3x. So those are some pretty good examples, I think. It doesn't seem like too terrible a question, but definitely you're going to have to do a little bit of adjusting for these problems, right? You're going to have to sometimes make a U sub before you do it. This one we didn't really do a U sub here. We just identified what was playing the role of each part. Usually X is playing the role of U, or sometimes it's like X squared or something else. So yeah, but the U is always the X thing. Okay, moving along. Try and keep the papers in order. Write the trapezoidal rule to approximate the integral of a function f on the interval from 1 to 5 using n equals 4 trapezoids. Cool. Not as bad as it looks. They didn't give us a function, right? They just said f of x. So here's what I would draw. Right? Because you said to draw something, yeah, draw a sketch. So I would draw some function that looked like this, just trying to make my life easy. And then there's 1 to 5. You know what I should have done? No. I wonder what kind of sketch. I feel like draw a sketch is not super nice here. It's like, does you want me to actually draw trapezoids as well? I wouldn't, but I guess maybe we should look at the solution. Have any of you looked at the solutions here? I'm curious what the solutions are doing, just because I'm curious. Let's take a look here real quick. Sorry. 1 second. Let me look at these solutions very quickly. What do you expect people to do here? Someone says something in the chat. He drew it like that. So, but he didn't draw like any trapezoids. Midterm 3 solutions. It's problem 3. Okay. He kind of drew some trapezoids. Okay. So what I would say is I would actually make my picture not quite this. I would make my curve more rounded. Not because we have to, but because it's easier to draw the trapezoids that look like they're not actually on the curve. So if it were me, I say that. If it were me, it's always me. It's no one else, James. It's just you. For me, I would draw it more like this. So it's kind of easier to then divide this up into 4 sections. And then for each section, you're trying to draw the trapezoid. And I'm trying to make it look like, okay, there's my trapezoid. There's my trapezoid. This one's kind of silly. There's my trapezoid. There's my trapezoid. Just so you're kind of showing the difference between like we're actually missing some area here. But again, as long as you've drawn something and then maybe like T1, T2, T3, T4, something like that. Okay, so then we know that our have I used terrible notation here? Let me check one thing. No, he did that too. Interesting. Okay. So what we would say then is their integral from 1 to 5 of f of x dx is approximately equal to our trapezoid error estimate. So that's going to be delta x over 2 times 1 times f of the first thing plus 2 times f of the next thing plus 2 times f of the next thing plus 2 times f of the next thing plus 1 times f of the last thing. Where these numbers are here are 1, 2, 3, 4, and 5, because again, you've got an easy delta x. Just 1. So really, I should have just plugged in my 1 right there and said this is just a 1 over 2. And that's all you can do. Right here, all we're going to do is say, great, you're going to get 1 over 2 times 1 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 2 times f of 4 plus 1 times f of 5. End the story. There's nothing else to be done. State the error formulas. So clearly in this practice exam, he is telling you these are formulas you have to know, right? He's definitely not going to give them to you. He's asking you to state them. So error formula, the absolute value of what do we say? En? I say En. Whatever. Is less than or equal to b minus a cubed over 12n squared times the max of the absolute value of the second derivative of f, where x is between a and b. Yeah, cool. Memorize it. That's all, right? That's all there is to say about that. You have to memorize it. Okay, so now for the questions that are a little bit more interesting. F of x equals x cubed. How large does n need to be since the error of the trapezoid rule approximation is less than 1/10? Cool. So let's deal with the f double prime part first. Let's see here. So let's find f double prime, but then I'm curious about something. So f prime of x is 3x squared. F double prime of x is 6x. I'm concerned. Okay. So this I find this personally tricky because I missed the part, or I forgot about the part that this is still part of the same problem and our intervals from 1 to 5. I forgot that part, but I needed that part, right? Because you have to say, great, there's my oh my gosh, there's my second derivative. So what's the max of the absolute value of my second derivative? Well, it depends on what our interval is, right? But we're on 1 to 5, so what value is going to what x should I pick to maximize that? I'm picking the 1, I'm picking the 5. 5. So if I plug in 5, that's going to be 6 times 5, which is 30. There's your max f double prime. So then I feel like I guess I don't know. I feel like there could be a little bit more room in this problem. To me, it feels like it's almost short enough. They're like, am I supposed to use like some sort of trick to do this really fast? Because there's so much. But no, I guess it's not that bad. So we're gonna have 5 minus 1 cubed over 12n squared times 30 should be less than 1/10. And now we're gonna solve for n. All right. So 4 cubed times 30 divided by 12n squared is less than 1/10. I'm gonna, what are you doing here? Oh, didn't finish the problem. He set it up. I don't see him finishing it. That's annoying. I'm annoyed by that. I'm gonna finish the problem. Right, because he said, how large does n need to be? I'm disappointed in you. Okay, so anyway, so I'm going to bring the n squared up there, the 10 up there. So I'm going to have that 4 cubed times 30 times 10 over 12 is less than n squared. And we could simplify this a little bit. 12 has a factor of 4. So I can cancel a 4 here, and one of the 4s there. And then that 3, well, the 30 divided by 3 is 10. This works out pretty nice. So see, he did come up with a problem where it actually works out nicely. So we have we have 4 squared times 10 is less than n squared. So we have that n is bigger than the square root of 16 times 100, which is going to be 40. Interesting. Yeah, and really, I suppose we should be using less than or equal to here. The reason why is because this is right, we have a less than or equal to right there. And so we're saying that this is less than something else. We'll certainly get that by this, that being less than or equal to. The reason I'm pointing that is because if you actually get an integer number here, like we're getting, you don't want to bump it up to the next integer. Whereas if you're getting a decimal, then you do have to round up to the next integer because you're talking about a number of integer things. So 40. I'm surprised the solutions here don't have the final, but whatever. That's how it is. And then estimate this integral with 2 trapezoids. 2 trapezoids? Okay, fine. Here's our function. Y equals x squared from 1 to 5. And then we're going to break it up into 2 trapezoids, so the middle is 3 there. So our trapezoid estimate is going to be our delta x, which is 2, divided by 2, times 1 times f of 1, plus 2 times f of 3, plus 1 times f of 5. Which makes sense, right? Because you're doing the average of these two. So you're getting f of 1 plus f of 3 divided by 2. And then you're doing the average of these two. You're getting f of 3 plus f of 5. So you're getting f of 3 twice. So that ends up equaling 1 times f of 1, which is 1, plus 2 times f of 3, which is 3 squared, plus 1 times f of 5, which is 5 squared. And that's something. You might even leave it like that if you were pressed for time. You can simplify this. It's 25 plus 18 plus 1. So I don't know, something. 44? I don't even know. He didn't solve it either. But right, it brings up a good point, right? Oh, ooh, he made a mistake though, I will point out. On his answer, he started at 0, not at 1. But he should have started at 1. Because the integral definitely says from 1 to 5, not from 0 to 5. So be careful. The answer here should really be 1 plus 18 plus 25, which is interesting. I will say, when you're writing solutions, it is easy to make mistakes because you're just trying to write them really fast. So I don't blame him for making a mistake. It just happens sometimes. That said, it's important to be careful when you're doing your work, right? Just because they made a mistake on the solution doesn't mean they're going to be forgiving if you make a mistake on your reasoning. So try not to make little mistakes. All right, let's do the next one. Average value. Average value is kind of like the best thing, not the best thing ever, but like you shouldn't be scared by it. You're just taking an integral and doing one little additional thing. So here's that point out. I would say that the integral from 1 to 4 of f of x dx is equal to x squared from 1 to 4, which is 4 squared minus 1 squared, which is 15. So the average value is just going to be 1 over 4 minus 1 times that same integral. You don't have to do it this part first. I just wanted to show you that you're just doing an integral and dividing by the length of the interval. So we're going to get 1 over 3 times the thing we just calculated, which is 15. Then we're going to get 5. Not too bad. Cool. More integrals. Integral of 5x squared. Oh, there's a chat. He said this wasn't on the midterm. Oh, okay. You mean average values? Okay. Even if it was, it's not that bad. You're literally just dividing by the length of the interval. But fair question. Or fair point. Thank you. Well, let's do this next one though. So this next one is a mixture again. You have a power of x times an e to the stuff. It's either going to be a u sub or integration by parts. I'm definitely looking for a u sub first, and it is a u sub. If you let u equal x cubed, the thing that's stuck in the exponent of the e to the something, your du is 3x squared dx. I'm going to get rid of that 3 because I don't have a nice 3 here. I'm going to say that 1/3 du is equal to x squared times dx. And I'm going to start replacing things. I'm going to rewrite this as equal to 5 times the integral of e to the x cubed times x squared dx. The x squared dx gets to be replaced by 1/3 times du, and the e to the x cubed gets to be e to the u. I'm going to rewrite my integral as 5 times the integral of e to the u times 1/3 du. I probably would have automatically brought out the 1/3, to be honest. I probably would have started by writing this as just 5/3 integral of e to the u du. We do actually have to do the integral when we're doing a u sub, right? I know the integral here is the same, but make sure you're saying, oh yeah, the integral of e to the u is 5/3 times e to the u plus c. And then we have to end with the variable we started with, so this is going to equal 5/3 times e to the x cubed. Let's see. I'm curious what the point of this next question is. But oh well. Here's how I would do this next question. I would just multiply it out. Right? If it's x plus 1 squared, x squared plus 2x plus 1, we can anti-differentiate that. We're going to get x cubed over 3 plus x squared plus x from -1 to 1. That's going to be 1/3 plus 1 minus -1 cubed is -1. So it's going to be -1/3 plus +1 because -1 squared is +1, and then -1. I would just cancel the 1 minus 1 there and say I've got 1/3 plus 1/3 is 2/3 plus 2. You could get a common denominator and say that your answer is 8/3. I don't really think you're required to do that. I am curious what you were for the solutions here. Oh, what this is? Did I make a, oh no, I'm looking at that. I'm like, the solution seems to be missing a page, or is it out of order? Solutions seem to be missing problem 4. Maybe because you said that this, but I mean, 4B and 4C should be fair, right? Those are questions that are totally valid. Okay, I don't know why they're missing from the solution. Oh well. No, not at all. Yeah, and I don't know why I didn't think of that, but that is the better way to do this. Thank you, Megan. You should write this as, yeah, brilliant, James. Good call. That should be just x plus 1 cubed over 3 from -1 to 1, which is then going to be 1 plus 1 cubed over 3 minus 0 cubed over 3, which is exactly 8/3, which is the same as 2/3 plus 6/3. So yeah, good call. That is for sure the way you should do this. No doubt about it. Question or something in the chat here. So you said you accidentally pasted it from the last midterm practice. Okay, well, those are still good questions. Let's look at problem 5. So obviously problem 5 is an improper integral, right? They're both has an infinity, even though it's improper. So the first thing you should do is write this as the limit as b goes to infinity of the integral from 5 to b of, I would rewrite this as 2x minus 1 to the -1/2. Now, personally, I think you can all do this integral without doing a u sub. Just like we should have done the last one without doing, or we did do the last one without doing a u sub. This one's slightly more complicated because instead of having x minus 1, I have 2x minus 1. I'm still going to use the reverse power rule though. I'm going to get 2x minus 1 to the -1/2 plus 1 is +1/2. And then I'm going to divide by 1/2. But I'm also going to divide by 2. So I'm dividing by 1/2 because of the power rule, right? I add 1 to my power, I divide by the new power. I'm dividing by 2 because that's the coefficient of x right there. And then we still need all the other machinery. So I still need the limit as b goes to infinity And the limit of integration from 5 to b. Let's make this look prettier. Let's write this as the limit as b goes to infinity. We're fortunate here, the 1/2 and the 2 cancel out. And we're just left with 2x minus 1 to the 1/2, or I would prefer to write the square root of 2x minus 1. Let's do a quick check. If we took the derivative of 2x minus 1 to the 1/2 power, would we get back 1 over the square root of 2x minus 1? Let's see. I would have 1/2 times 2x minus 1 to the negative 1/2, and then the chain rule said I'd multiply by 2. Oh yeah, those are the same. 2x minus 1 to the negative 1/2 is 1 over the square root of 2x minus 1. And we didn't have to do that, but I felt a little shaky about my antiderivative, so I wanted to check. This 2 here. So let me ask you, if I was going to do the integral of cosine of 4x, what would that be? Where'd the 1/4 come from? Right, so it's really coming from a u substitution, but we're not going to do it. So here's the deal. If I said the integral was just sine of 4x, what's the derivative of sine of 4x? Megan, what's the derivative of sine of 4x? Of 4x times 4. But the problem is, I don't have a times 4 here. And for the derivative of this to be that, which it should be if this is the antiderivative of that, we have to have a 1/4 here. So when we take the derivative of this, we actually get the thing we were anti-differentiating in the first place. So that's why I ended up dividing by 4 or multiplying by 1/4, because we need to account for the eventual chain rule. You could also do it as a u sub though. You could really let u equal 4x. du would be 4 times dx. 1/4 du would equal dx. And then you could rewrite this integral as 1/4 the integral of cosine of u du. And then we integrate. The integral of cosine of u is just sine of u. And then we plug back in our u and get 1/4 times sine of 4x. But the shortcut, which we're using here, is that when you integrate something and you have a coefficient of x, you end up dividing by that coefficient of x. So here we had a 4 times x, we end up dividing by 4. Here we have a 2 times x, we end up dividing by 2. Sorry, dividing by 2. And then that 1/2 we're dividing by is because of the power. Okay. So then to finish this off, we plug in our limits of integration. We're not taking the limit yet. The limit's like the very last thing you do. So we still have the limit as b goes to infinity, and then we have the square root of 2 times b minus 1 minus the square root of 2 times 5 minus 1. And then as b goes to infinity, what happens to the square root of 2 times b minus 1? Does it go to a finite number, or does it also go to infinity? If the insides are getting really, really, really big, you take the square root of that. Is it still really big? It still is really big. So this limit is infinity, which means we have a divergent interval. Okay. Let's look at the next one. If I had to guess, I would guess the next one's going to converge, just because usually if I'm asking you 2 of these questions, I'm going to make one of them diverge and one of them converge. Not that you should count on that, but it's something that's there in the back. You're like, oh, the next one's probably going to diverge. That's what I'm looking at. So let's do this one. So we're first going to write the limit is a approaches negative infinity of the integral from a to -1. And I would rewrite this as x to the -2. Now let's integrate. We're going to get, we still have to write everything out. The limit is a goes to negative infinity. The integral of x to the -2 is x to the -1 over -1 from a to -1. I always want to rewrite this fraction. I don't want negative powers. So I'm going to rewrite this as the limit as a goes to negative infinity of 1 over -1 times x from a to -1. Normally I would have just put the negative out in front. I just wanted to show you that like there's a reason that's happening, right? It doesn't magically happen, it's because divided by -1 is the same as multiplied by -1. So here we're gonna get the limit as a goes to -infinity. I'm gonna plug in the -1. I'm gonna get 1 over -1 times -1 minus 1 over -1 times a. And now, if a goes to -infinity, I have 1 over a number that is very, very, very large, which means that's going to go to 0. So I'm going to get 1 minus 0, which is 1. So this interval converges. I would encourage you to write those words. Like if your integral is infinity or -infinity or does not exist, which usually doesn't happen, write that it diverges. If your integral is 1 or 2 or pi or -17e squared, write that your integral converges because it's converging to a finite value. Cool. What's on page 6 here? More integrals. These look like partial fractions. All right, I know it's 11:48. I'm going to finish these off. If you need to go, you're welcome to go. You're also welcome to stay though. So we'll finish these off and then we'll wrap it up. Well, we'll be done. So here I'm going to see that this looks like x times x plus 1. Fun fact, you could probably use an integral table for this one, but I know that's not what he wants us to do. So we shouldn't use the integral tables if we're not supposed to use them. So here we're going to have 1 over x times x plus 1 equals a over x plus b over x plus 1. Multiply both sides by the common denominator and get 1 on the left equal to a times x plus 1 plus b times x. I would always suggest, sorry, someone asked a question. What would be a case where the integral wouldn't exist? Like if you had the integral from 1 to infinity of like sine, the integral would be cosine, and if the limit as b goes to infinity of cosine of b, that limit doesn't exist. So that's a good example of where an integral would not exist. I would always suggest using the convenient values of x method that I've talked about a few times, where you just pick nice numbers for x. So we let x equal -1, then you have 1 equal to a times 0 plus b times -1. So -1 is equal to b. We let x equals 0, you get 1 equal to a times 1 plus b times 0. So a is equal to 1. You're always just picking the values. So, but by the way, the convenient values are just the values that would make the denominators equal to 0 in this original expression here. So x equal to 0 because a over 0 is undefined. X equal to -1 because -1 plus 1 is 0 and b over 0. So pick the values that make this expression undefined. I know it's kind of a weird way of picking things, but it totally works. Plug back in. So now we're integrating a over x, so 1 over x minus 1 over x plus 1. This is going to equal the natural log of the opposite value of x minus the natural log of the opposite value of x plus 1 plus c. Cool. One thing I would note about all these partial fractions questions is none of them are making you do polynomial division first. None of them have a degree on top that is greater than or equal to the degree on the bottom. That doesn't mean you won't be faced with that potentially, but just something to be aware of, right? So if your degree on top was greater than or equal to your degree on the bottom, you would do polynomial division first. All right, so here I'm hopeful that the denominator factors, it does x plus 2 times x minus 1. That's going to be a over x plus 2 plus b over x minus 1. We're going to rewrite this as 3 equal to a times x minus 1 plus b times x plus 2. I'm not showing the step of multiplying both sides by the common denominator, mostly because I don't have enough room on this page to do it. But, right, that's what we're doing. We're multiplying both sides by the common denominator x plus 2 times x minus 1. Same deal here. I'm going to use the convenient values of x. If I let x equal to 1, I have 3 on the left equal to a times 0 plus b times 3. So I get b equal to 1. If I let x equal -2, I get 3 on the left equal to a times -2 minus 1, which is -3. So 3 divided by -3 gives me that -1 is equal to a. How nice. So then our integral is going to be the integral of -1 over x plus 2 plus 1 over x minus 1, which is going to equal negative natural log of the absolute value of x plus 2 plus the natural log of the absolute value of x minus 1. Let's see. So as long as you're integrating a constant divided by x plus or minus something, you just get that constant times the natural log of the absolute value of x plus or minus whatever. Finally, this last one, which is going to be a little bit meatier here. So I'm going to rewrite this as 4x squared plus 2x minus 1 over x squared times x plus 1. Okay, let me ask everybody, show me on your fingers or write in the chat, how many fractions are going to be in my partial fraction decomposition? Yeah, show me on your fingers. How many? Yep, that many. Exactly. 3. We're going to have an a over x squared, a b over x, because you have to have all the lesser powers of any repeated factor, and finally a c over x plus 1. I will point out, when we integrate c over x plus 1, it's going to be c times the natural log of the absolute value of x plus 1. When we integrate b over x, it's going to be b times the natural log of the absolute value of x. But when we integrate a over x squared, it's going to be a times x to the -1 over -1, because that's how you integrate x to the -2. So we have to find a, b, and c. Great. So we're going to have 4x squared plus 2x minus 1 equal to a times x plus 1. So I did a bad job here of giving myself enough room. Plus b times x plus 1. That's terrible. Plus c times x squared. Sorry about that. That looks awful. Let's use our nice value. So we have x equal to -1 as a nice value. So we have to, here you also have to plug in the value on the left as well, right? In the previous examples, we didn't have to because our left-hand side was just a constant. It's not the case here. So if I plug in -1, I'm going to get 4 plus 2 times -1 minus 1 equal to a times 0 plus b times -1 times 0 plus c times -1 squared. Or in other words, 4 minus 2 minus 1, so 1 equals c. Because if I multiply both sides by the common denominator, the x squared will cancel. Right, so when I distribute that there, the x squared cancels and you're left with a times x plus 1. Whereas you multiply that here, one of the x's cancels and you're left with b times x plus 1. When we multiply here, the x plus 1 cancels and you're left with c times x squared. So then using the other convenient value of x, which is 0, we're going to get 0 plus 0 minus 1 on the left equal to a times 1 plus b times 0 plus c times 0. So a equals -1. And then finally, we are out of convenient values. That's when we start looking at the highest power of things. So I would look at x squared. So for x squared, there's 4x squared on the left. There's not an ax squared, but there is a b times x times x. So there would be a b times x squared, and there would be a c times x squared. So 4 is equal to b plus c. So c is also equal to what? Oh, sorry. Nope. C is also equal to what? Sorry. C is equal to 1. So b should be equal to what? Right. And then we can do our integral. We're going to have the integral of -1 over x squared plus 3 over x plus 1 over x plus 1. So you're going to get, I might rewrite this. I'm going to think of that as negative x to the -2. So when I integrate, I'm going to get negative x to the -1 divided by -1 plus 3 natural log of the absolute value of x plus 1 times the natural log of the absolute value of x plus 1. Let's see. And if you really wanted to, you could rewrite this. Oh, no, not if you really wanted to. We do have to rewrite this because we said no negative powers, which is hard for me to remember, I'll be honest. I would rewrite this as +1 over x plus 3 natural log of the absolute value of x plus the natural log of the absolute value of x plus 1. Let's see. Cool.